Okay, my dears, so I'm going to record the audio over this video because I know that I posted this video without any audio, which was super fun for all of us because it is half an hour and it took 5 hours to upload, but it's okay. I'm just gonna bear with it. So this is going to go over the answers to the monohybrid practice problems. I know a number of you had some issues with that, and it is really important that you understand how to do these monohybrid practice problems because it's only going to get more complicated from here, right? So it's important that you understand how to do these. So I'm going to go over all these answers so that you can sort of figure out what's going on here. Okay. Just a titch behind. Okay. So we're going to go over this first problem, right? So in tomatoes, capital R is dominant and lowercase r is recessive, meaning that red fruit will override yellow fruit, right? So I'm going to underline that. And I just want to remind you that the R's, right? Those are the genotypes. The single letters are known as the genotypes, whereas the trait, red or yellow, right, what you're actually seeing is known as the phenotype, right? That's a good reminder. So now we're going to cross two tomato plants. And the first tomato plant, the first one of the parents, is homozygous red, right? And homozygous means the same, right? So two letters that are the same. And since it's red, it's dominant. So it's two capital R's. And then we're also going to do a yellow fruit, right? And we know that yellow is recessive, and the only way for it to be recessive is if it's homozygous recessive, so it's two lowercase r's, right? So we have the parents. The parents are homozygous dominant by homozygous recessive. And it's asking what is the phenotypes of the F1, the offspring, right? Remember that F1 means offspring. So we're going to type one parent into the top, right? And one parent on the side of our Punnett table. So parent 1 is up there at the top, two capital R's, and parent 2 is on the side, and it's going to be two lowercase r's, right? The Punnett table is just a tool for figuring this out. And then we cross that, so it's heterozygous. Oh, that was an error. Don't know why I did that. So it's going to be 2, and then it's going to be heterozygous again, and heterozygous again, right? So we look at all of our individuals, and they are all heterozygous, right? So the phenotypes of the F1 offspring of the parent generation, it's all going to be capital R. The only possible phenotype, right, because it's heterozygous, is red, right? Because when something's heterozygous, the dominant trait is overriding, right? So if there's only heterozygous, then there's only going to be red, right? There's no yellow, it's only red, because that capital R is overriding the lowercase r. Okay. And I'm going to just write in those phenotypes as well into our table. That's something you can do if you're feeling a little confused about what to do next. Write in your genotypes and write in your phenotypes. Right? And then it asks, what is the genotype and phenotype ratio? So we've done part A. We're good to go. What am I going to do next? I was asking what is the genotype and phenotype ratio of the F2 generation, although I'm pretty sure I made an error here and thought it said the F1 generation. My mistake, but I am going to show you how to do the genotype ratios, right? So I'm saying this is 100% heterozygous, so you can totally write it as 100% heterozygous, right? Because the only thing we have are R, capital R, lowercase r, which also means the phenotype is 100% red, right? You can also write the ratio as 4 heterozygous to 0 homozygous dominant to 0 homozygous recessive. And you can write the phenotype ratio. Remember the genotype ratio is letters, phenotype ratio is traits. You can also write the phenotype ratio as 4 red to 0 yellow. Again, I made an error here in that it is not, for B, I did not do the F2 generation, I just stuck with the F1 generation. My mistake. It's okay, we'll get there. So that is the final answer, right? The genotype ratio and the phenotype ratio. Okay, so that's the answer to problem 1. We're going to scroll down to problem 2. I'm trying to go through this pretty quickly because I know it's a long video, but we will get there. Okay, so here we're talking about cattle here. We're talking about the capital H hornless and lowercase h horned. I'm sorry for the background noise. So we're going to have a homozygous dominant cow, which means the same letter, right? The same allele, which is the same word for letter, which is capital H, and we have a homozygous recessive, which is a lowercase and lowercase letter, right? So we have homozygous recessive, and then we have homozygous dominant. So it's asking us what will be the genotype and phenotype ratio of the F1 generation. So it's just like the problem above. We are gonna go and put this into our Punnett square, right? So parent 1 goes on top, which is our homozygous dominant, and parent 2 goes to the side, which is our recessive, or homozygous recessive, and it doesn't matter which one you put on which side, and then we fill in the genotypes, right? So we can fill in our genotype ratio, right? Because it looks like all of our offspring, well, we're going to put in our phenotypes first, sorry. So it looks like we're going to put in our offspring, so when it's heterozygous, that dominant trait is going to override, right? So all of those heterozygous individuals are going to appear hornless, right? So we're appearing hornless. So when we go to our ratios, our genotype ratio, right, is going to be 100% heterozygous, right? Because all of them are uppercase H, lowercase h, and when our phenotype ratio is 100% hornless, because all of them are 100% hornless. So I circle that. Remember, we're just focusing on the offspring, right? We're not worried about the parents. The parents are just there to set up our Punnett square. They have nothing to do with the ratios, right? The parents have nothing to do with the ratios. As you can see, I am crossing those out for us. Yes, so helpful, thank you. Okay, so now we're gonna scroll down to part B. And so in part B, it gets a little bit more complicated. It's saying if one of the offspring is mated to the hornless parent, what phenotypes would they produce? And yes, it's a little bit of incest, but just bear with me. So we want to remind ourselves that the F1 generation is 100% heterozygous and 100% hornless, right? So, oops, I'm going to have to type that in again. Oh, wow. I'm really struggling right here, aren't I? Okay, so it's 100% heterozygous and 100% hornless. Okay, so it's going to say, if we take one of those F1s, right, which we know that F1 generation, right, is heterozygous. So we can put that genotype in. It's really helpful to put in the genotypes as you read through the problem. And that's going to be mated to a hornless parent, to the hornless parent. We know that the hornless parent is capital H, right? We know that from part A. The hornless parent. So then we're going to make that's the cross we're going to have, homozygous dominant by heterozygous. And they want to know what phenotypes could we produce. So we're going to do our Punnett table. Right? So we're going to stick our homozygous dominant on the top and our heterozygous on the side. Again, it doesn't matter which one you put where. So that's our hornless parent, and this is our offspring, or our F1 right, parent. And so then we're going to put those together, and we're going to get 2 homozygous dominant and 2 heterozygous, right? So that would be our phenotype ratio, but we don't have to write that. It just wants to know what phenotypes could they produce, right? But we know that that homozygous dominant is going to produce hornless, and we also know that that heterozygous is going to produce hornless, right? So we're going to write those in. Both of those are just going to produce a hornless phenotype, right? So we know that the only possible phenotype that cross could produce is a hornless. That's not the only possible genotype, but it is the only possible phenotype, right? The actual trait. Okay, we're going to go down to C, right? So in C, it asks if one of the offspring, turn that off, if one of the offspring, which we found in part A, right, is mated to the horned parent, what happens? So we know the offspring, the F1, is heterozygous, and the horned parent, we know if it's horned, it's gotta be lowercase, right? Recessive. So we put in those 2 genotypes, and again, it's asking what are the possible phenotypes. So then we're gonna use our Punnett square, and we're gonna do the cross heterozygous with homozygous recessive, right? So we're putting that, oh, I don't know what's happening. Okay, we're putting that into the top of the table, right? So put our cross into the table. And we're going to fill out our Punnett square, right? So again, the parents are on the top and side, and the possible children are in the middle. And what we see, we're going to fill in our phenotypes, right? So a heterozygous is going to be hornless, but this recessive, finally it's going to be a horned individual, right? So we have 2 possible phenotypes for this cross, hornless and horned, right? So it has 2 possible phenotypes for this cross, hornless and horned. It's not just one. So this is new, and that we're done with that problem. Woohoo! Okay, I'm gonna figure this out. Okay, so now we are on to problem, it says problem 2, but it's really problem 3. Clearly I'm having a little bit of error there. Okay, so I'm gonna zoom out so I can fit the whole thing. So we're gonna talk about polycystic kidneys, and that's dramatic, but it just means a certain type of disease that is genetic. But we know that a capital P, right, is dominant, and so polycystic kidneys are dominant, right? So we see that. And normal kidneys are recessive. So we want to fill in, the first question is what are the genotypes? So we know that the homozygous dominant is going to be capital P, capital P. Remember, it's asking for the genotypes, the letters. Heterozygous, capital P, lowercase p, and homozygous recessive, lowercase, lowercase. Oh, I did that again, didn't I? Okay, I have to rewrite this because I don't know how to do technology, clearly. Okay, so now it asks, show a Punnett square between a heterozygous parent, which we know is going to be uppercase, lowercase, and a homozygous recessive, lowercase, lowercase. So we're gonna fill in that Punnett square. Okay, one parent on top, one parent on the side, right? And then fill in, I know it's hard to read the P's, but I'm gonna fill in that. And then it asks just simply the genotype and phenotype ratio, right? So let's take a look at what we've got. We know we have 2 heterozygous to 2 homozygous recessive. You can also write this, totally correct either way, as 50% heterozygous or 50% homozygous recessive. The phenotype ratio, so we're going to write in some phenotypes. So that heterozygous phenotype is going to be polycystic, right? Because that if there's one dominant, it's going to override. Whereas the recessive is just going to be a normal kidney, right? So there's 2 polycystic to 2 normal. You can also write this as 50% polycystic to 50% normal. Okay, and that is the answer to 3. That was easy. I'm just going to underline these. I don't know why, can't remember. Okay, so then we're going to scroll down and we're going to go to this next problem. Okay, we only have a few more. So this next problem, okay, so it says, when a brown mink, minks are like weasels, when a brown mink was crossed with a white mink, all of the offspring were brown. So we have a brown mink and a white mink, all of the offspring were brown. And that tells us immediately that if all the offspring are brown, when a brown and a white are crossed, then we know that the brown is dominant, right? Because we're not seeing any of that. So we know that the brown is dominant. And the ratio of that, when the F1 interbreed, the results are 33 brown and 10 white, right? So when we look at that 33 to 10 ratio, what we see is a 3 to 1, right? If we reduce that 33 to 10, it's not perfect because real life is never perfect, but approximately a 3 to 1 ratio, right? Which means that there are going to be 3 brown to 1 white mink, right? We're talking about the coat color of these weasel creatures. Okay, and because there's more brown than white, that's a good indicator as well that it's going to be brown that is the dominant allele. We also know it's brown because when we cross a brown and white, we only get brown, right? So that brown is overriding, it's the dominant. So now it wants the genotypes of the original brown and white mink and the F1, right? And we're going to use BB as our letters for our genotypes. Okay, so here we go. We're going to get started. So the first thing we need to figure out is our F1 generations, right? So we need to figure out what, we're going to use Punnett squares. I'm going to make one right here. We need to figure out what parent genotypes are going to give us a ratio of 3 brown to 1 white, right? What are the genotypes that are going to give us that? So we're going to just test different genotype combinations. We know that if we combine homozygous dominant with homozygous dominant, all of those are going to be brown, right? There's not even a white allele in there. There's no possible way it could be a white allele. We also know if we combine a homozygous dominant with a heterozygous, there's only 1 white allele, so there's no way to have 2 lowercase b's that we need, right? For it to be white, we need it to be 2 lowercase b's, and there's no 2 lowercase b's in that option, so there can't be any white either. There can't be any white there either. So now we're going to try our third option. We haven't even needed to use a Punnett square yet. Okay, so in this option, you could have, there are 2 lowercase b's, so maybe this is our option. So we're going to try it in our Punnett square. So we're going to put our BB in there and our homozygous up there and our homozygous dominant at the top, homozygous recessive to the side, fill in our Punnett square, and we're getting 100% heterozygous, which is 100% brown, right? And that is not fitting our ratio, right? So we know that that combination of parents also does not work. Does not work. Does not give us any white individuals. And we need at that 3 to 1 ratio. So now we're going to try another combination. We're just trial and error going through these different combinations. We're going to put that one in our Punnett square. Heterozygous in the top, homozygous recessive to the side. We're going to fill that in. Hard to read. Fill that in. We are getting some white individuals finally, right? So we get that lowercase b. That means that they're going to be white, homozygous recessive. That's a good sign. But the ratio is 2. The ratio is going to be 2 heterozygous or 2 brown to 2 white, right? So that's not the ratio that we want. That's still not the ratio that we want. That's the wrong ratio. We're looking for the 3-to-1. Right? We're saying that one only gives us 50% white to 50% brown. So we're going to try another one finally. So we're going to do BB times BB, or heterozygous by heterozygous. We're going to plug that one in. And we're going to see what we get. Oh, maybe this one worked. As you can see, that homozygous dominant is going to be brown, and so are the heterozygous. So we actually have 3 brown to 1 white, and that is going to be our F1. We figured out the F1 parents, right? So the F1 parents are heterozygous by heterozygous. That will give us that ratio in the F2, right? So we figured that out. But now we need to figure out, what are the parents, right? How are we going to get 100%? How did we get that heterozygous by heterozygous, right? So that we crossed 2 F1s, and how did we get 100% heterozygous? We know it's 100% heterozygous because that's the only option for F1, right? So we're working backwards over the last 3 problems we did, right? It's a little more complicated. It's harder to understand. So we need to figure out what parents will give us 100% heterozygous. And I just go ahead and fill in what we know from the other problems, right? Because I know the ratios, and over time you'll get to know the ratios. And we figured out that to get 100% heterozygous, you need 1 parent homozygous dominant and 1 parent homozygous recessive. And that gives us the F1 generation. So we were given the F2 generation. We found the F1 through trial and error, and then we found the parent even faster just from previous knowledge. So this working backwards is a lot harder. It's just a lot of trial and error, but it's totally feasible. We're using that Punnett square as a tool. Okay, so now here we are in part 4. I'm going to show you another way to work backwards. Sally has dry, crumbly earwax, a recessive condition. So we're going to use E's, right? Because it's recessive, we know that genotype is going to be lowercase e, lowercase e. And Mel has wet, sticky earwax. So we know that's dominant, so her genotype could either be heterozygous or homozygous dominant. It could be either, we don't know yet, right? But their first child has dry, crumbly, right, which is recessive. So we know their first child is lowercase e, lowercase e. Right, so our question is Mel homozygous or heterozygous? How do you know, right? Is she that capital E, lowercase e, or capital E, capital E? How do we know? So we're going to, since there's a Punnett table, we're going to fill that in, right? But we're going to fill it in a different way. We know that one of their children is lowercase e, right? That's Polly. We know that genotype because she's recessive. That will help us fill in the rest of the table. So we know that to have that, it has to come from the parents, right? So we're working backwards. We're filling in the children to get the parents. So that we know that there's a lowercase e in both of those parent boxes, right? And we know that Sally is recessive, so she has to be lowercase e, and Mel is dominant, right? So the other allele for Mel's genotype has to be, right here I'm going to write Mel is, oh, no, I'm just going to write Mel. Okay, so, right? So we know that Mel has to have at least one lowercase e, and the other allele, of course, needs to be capital because she is showing the dominant phenotype. So her genotype has to have at least one capital in it. And so we know that Mel's genotype, the rest of it doesn't even matter, we know that Mel's genotype is heterozygous. Do you see how we worked backwards using our Punnett square to figure that out? Mel is heterozygous, right? One capital E, one lowercase e, because that's the only way they could have produced a child who was heterozygous. So we worked backwards using that skill of the Punnett square, or that tool of the Punnett square. The next one, Sally's expecting another child. There's a greater chance that it will have wet, sticky earwax, right, which is our dominant, or dry, crumbly earwax, which is our recessive? Which one is the greater chance? Okay, so now we need to fill in the rest of our Punnett table. So we go ahead and do that. A little hard to see. And we see that there's 50% chance of EE, which is our dominant, so it's wet, sticky earwax. And we have a 50% chance of recessive, right? Dry, crumbly earwax. So there's a 50% chance that the child either has wet, sticky earwax or dry, crumbly earwax. I know it's kind of a gross one, guys, but woohoo! Done with that problem. Okay, so I believe this is our last problem. Yes, thank God. Okay, so here we are again. So we're going to figure out, we have a capital B for brown eyes. That's our dominant trait. We know that because it's a capital, right? And lowercase b is blue eyes. That's our recessive trait. So what we're going to do is we're going to combine two heterozygous, right? So that's 2, capital B, lowercase b, and they produce 12 kids. How many will have brown eyes, blue eyes? So we're going to fill in our 2 heterozygous, right? And we're going to write that ratio. What is our ratio of genotypes and phenotypes? So we're going to plug in our phenotypes, right? So we know that that's brown, and this heterozygous one is also going to be brown because that dominant trait overrides the recessive trait. I'm just going to repeat that till the end of time. And we do have one blue child, right? One blue-eyed child. So we're going to write our little ratio. So we have a phenotype ratio. Always a good thing to do. If you don't know what to do, start writing your ratios. 3 brown to 1 blue, right? So we know that 12 kids. So we know we can turn this 3 brown to 1 blue. Another way to write that is 75% brown, 25% blue. So if they have 12 kids, we can expect 75% of them to have brown eyes, right? 75% of the 12 should have brown eyes according to this ratio, which is 9 kids. 75% of 12 is 9. And so 9 kids should have brown eyes. And then we can figure out 25% of those kids should have blue eyes, right? So that's 3 kids. So we can fill that in. I've stupidly written the heterozygous genotype in there. What it's really asking for is the number of kids with heterozygous genotypes. Half the kids, right, should have the heterozygous genotype, which would be 6. But I have written capital B, lowercase b into the heterozygous genotype question. That's okay. So let's see. If a couple has 3 children with blue eyes and 3 children with brown eyes, what is the most likely or the probable genotype of the parents, right? So 3 to 3, 50% brown, 50% blue. I've written E's. Wow. Oh, that's a little frustrating. It should be B's, but so we know that 50% are blue, right? So we're just going to plug in that EE, that lowercase e, into the children, right? We're just working backwards again. And then we're going to put in heterozygous. Right? So we've just worked backwards using the children's ratios, right? To figure out the parent genotypes. And that's the only possible one that works to make those accurate children ratios, right? And you can, I sort of knew how to do that, but you can definitely do some trial and error and make sure you're getting that ratio correct. But using the Punnett squares, both forward and backwards, is a really important tool to be able to figure out how to solve these monohybrid practice problems.